Hello everyone, welcome back to Next Gen Chemophiles. In our previous video, we studied Werner's coordination theory, which explained primary valency, secondary valency, and the coordination sphere. However, Werner's theory could not explain an important question. Why are coordination compounds colored? Why are some complexes magnetic? And why do some complexes become more stable than others? To answer these questions, crystal field theory, or CFT, was developed. Crystal field theory was proposed mainly by Hans Bethe and later developed by Van Vleck. According to CFT, ligands are treated as point charges or point dipoles. When these ligands approach a central metal ion, they interact with the metal's d-orbitals. This interaction causes the d-orbitals to split into groups of different energies. This is called crystal field splitting. Before ligands approach, all 5 d-orbitals have the same energy. After ligands approach, some d-orbitals become higher in energy, while others become lower in energy. In a free metal ion, the 5 d-orbitals are dxy, dyz, dzx, dx square minus y square, and dz square. These orbitals have the same energy and are called degenerate orbitals. The most common geometry is the octahedral complex. Here, 6 ligands approach along the x, y, and z axes. The d-orbitals split into 2 groups. Lower energy group, T2g. These are dxy, dyz, dzx. These orbitals lie between the axes, so they experience less repulsion. Higher energy group, e.g. these are dx square minus y square and dz square. These orbitals point directly toward the ligands, so they experience greater repulsion. The energy difference between these two groups is called delta, or the octahedral crystal field splitting energy. Electrons first occupy the lower energy T2g orbitals. Whether they pair up or move to the higher energy orbitals depends on 2 factors: crystal field splitting energy, delta, and pairing energy, p. High spin and low spin complexes. If delta is smaller than the pairing energy, electrons prefer to remain unpaired. This forms a high spin complex. If delta is larger than the pairing energy, electrons pair in the T2g orbitals first. This forms a low spin complex. When electrons occupy the lower energy T2g orbitals, the complex becomes more stable. This extra stability is called crystal field stabilization energy, or CFSE. Greater CFSE means greater stability. CFT also explains the magnetic behavior of complexes. If unpaired electrons are present, the complex is paramagnetic. If all electrons are paired, the complex is diamagnetic. For example, strong field ligands like Cn- often produce low spin complexes, while weak field ligands like F- usually produce high spin complexes. One of the biggest successes of CFT is explaining color. When white light falls on a complex, electrons absorb energy equal to delta and jump from T2g to Eg orbitals. The remaining light is transmitted or reflected, and we observe the complementary color. This electronic transition is called the DD transition. CFT successfully explains 1. Color of coordination compounds. 2. Magnetic properties. 3. Crystal field splitting. 4. High spin and low spin complexes. 5. Crystal field stabilization energy. However, CFT also has some limitations. It assumes that metal-ligand interactions are purely electrostatic. It cannot fully explain 1. Covalent character of bonding. 2. The spectrochemical series in detail. 3. Pi bonding between metals and ligands. These limitations were later addressed by ligand field theory and molecular orbital theory. Let's summarize. In crystal field theory, ligands cause the splitting of d orbitals into different energy levels. In an octahedral complex, T2g orbitals have lower energy and Eg orbitals have higher energy. The magnitude of delta determines electron arrangement, magnetic properties, color, and stability. Crystal field theory is one of the most important theories in coordination chemistry because it connects structure, color, magnetism, and stability in a single framework. If you found this video helpful, like, share, and subscribe to Next Gen Chemophiles. Thank you for watching.